students, welcome to our class. Today we will discuss one of the very interesting topic, that is the utility of metal-carbene catalysts in alkene polymerizations. So, we have discussed the versatile reactions by the alkene by the metal-carbene catalysts, and you saw that different type of alkene metathesis reactions is possible by a single category of metal-carbene catalyst, like ring opening, ring closing, cross metathesis. Okay, and today we will discuss how applicable it is a ring in the polymerizations. Okay, and it is the reaction is very much similar what we have discussed in the last class. Okay, so today we will cover the concept like alkene polymerization by metal-carbene catalysts, its scope, and obviously the mechanism. Okay, so and the key points we'll discuss: the ring opening metathesis polymerization, its living polymerization nature, how it is living. Okay, and what is the advantage of living nature of this polymers catalyzed by the metal-carbene catalysts, and also we'll discuss very much similar, okay, but not ROMP, but very much similar polymerization which is also initiated by metal-carbene catalyst, that is called the ADMT. Okay, so that we'll discuss. Okay, so let's see how what are the catalysts which can do the polymerizations. Okay, so what is the ROMP? First we should discuss that ROMP is the ring opening metathesis polymerizations. So we have discussed the ring opening metathesis reactions where one cyclic alkene can be converted to a acyclic alkene. So here it is very much similar to the ring opening metathesis, but here you will see that we will get the polymer. Okay, so one example here you will see that dicyclo is a derivative of dicyclopentadiene. So here you will see that if you use the catalysts like Grab's catalysts, you will see that it is undergoes the polymerization reactions. Very much similar here you will see that is the cyclooctene. Okay, so this is nothing but cyclooctene. So if you take a suitable catalysts which can initiate the polymerization, and you will get this polymer. What are the catalysts? These are the most the catalysts are mostly used for the metathesis polymerization. Here you will see the Grab's first generation catalyst, second generation catalysts. Okay, and the reactivity actually increases from left to right, and you will see that after few slides I'll discuss that how you can choose your catalyst. Suppose if one alkene, cyclic alkene, is very reactive, then you can use the Grab's first generation catalyst. If it is moderately reactive or less reactive, you can use the second or third generation Grab's catalyst, like that. Okay, so let's here you will see some of the examples. Here is, and why it is so famous, because it's an enormous opportunity in polymer synthesis. Okay, and it is one of the very key points that it is a compatible with various functional moieties, even the biofunctional groups. Okay, such as sugar, amino acids. Okay, like that. And here you will see if it is this kind of where the R groups are sugar, amino acid, then also there is no problem in the polymerization. So you can get the polymers with bifunctional moiety by using the Grab's catalysts or using the metal-carbene catalysts. Okay, so here you need what you need a cyclic monomer is cyclic alkene. Okay, okay, and a suitable catalyst, okay, and you have to choose the catalyst according to the ring strain associated with the cyclic alkanes. I will discuss in later parts. And one of the very important feature of this or advantageous feature is that uh, the polymerization is living, that we'll discuss when I will discuss the mechanism, and the um, the and also the narrow molecular weight range. That means the PDI is kind of 1.1 to 1.3. That is actually remarkable. So by using this, so it actually proves that this polymerization is actually living. Okay, so that we'll discuss. So from these slides, you will understand that this kind of catalyst, how it can polymerize the suitable cyclic alkanes through the ring opening metathesis reactions. Okay, so here you will see carefully that what is happening, although I will discuss the mechanism after some time. And here you will see that this is the catalyst, that is the metal-carbene catalyst. Okay, it may be Grubbs catalyst or also Stock catalyst, and this is this is called Norbornene. Okay, this is a cyclic alkene. So this is basically my monomer, and what happens, you will see here, this first initiated, okay, and so it's actually reacts like this one. Okay, so it forms a metallocyclobutane first, that I'll discuss later. Okay, and then forms a new metal-carbene. The mechanism is very much the same as we discussed in the last class for ring opening metathesis, and then again it reacts with the new metal-carbene center, and it forms and it's repeats, that is the propagation, okay, and forms your polymer. Okay, as we discussed that this polymerization not only depends, okay, depends on the factors, okay, on definitely the electronic nature of catalyst, also depends on the monomer ring strain. As example, that if you use the cyclobutane, the reactivity is much higher than the cyclopentene or the norbornene. Okay, so this is the trend of the reactivity. So it clearly tells that it depends on the ring strain. However, we can also polymerize this one very nicely using let's say Grubbs generation 2 catalysts. Okay, so but the reactivity obviously will be little slower than the like cyclobutane. Okay, and as mentioned in the last slide, the PDI is quite narrow. Okay, narrow. That means the narrow molecular weight distribution, that is definitely is very advantageous, because you get very well defined polymer. Okay, and as it is a living, so you can control the architecture. If you remember, in the very beginning of the classes, that to control the architecture, the living polymerization is must. Then only you can make your desired block copolymers or different type of complex architectures. Okay, comb, brush, like that. So these are very much important, all that very advantageous properties of the ring opening metathesis polymerization by the metal carbene catalyst, and that's why it is becoming a very popular, okay, even not only for academic laboratories but also in industries, okay, the polymerization industries, various for different type of, which are mainly the with the alkenes with different functional groups, where we have to make a polymers or oligomers or cyclic or polymers. The metal carbene is obvious choice as a catalyst, okay, where the other metal or other polymerization like anionic polymerization or free radical polymerization, which are difficult in presence of the functional groups. So that's why it's becoming very popular in polymer industries, okay. Fine. So here is the mechanism. So here what you just check what is happening here. So this is my the cyclic alkene, that is the monomer, okay. I have drawn it in a cartoon form, okay, to understand. So what is happening here, you will see that the first is forming. So this is basically the ring opening metathesis polymerization. Obviously it's a just a reverse of the ring closing metathesis polymerization. So it's basically, you can think as a reverse of ring closing metathesis polymerization, okay. So here what is happening here, you will see the metal carbene first reacts with, okay. So here what is happening, so here you will see that first metal carbene reacts with cyclic alkene, that is my monomer, okay, and forms a metallocyclobutane intermediate, okay. And you will see this is actually bicyclic, this is 1 and this is 2, okay. So it is actually the bicyclic, one is alkene, one is the alkene cycle and one is the metallocyclo, okay. And then, okay, you will see that cleavage, and this cleavage is basically the cleavage of the metallocyclobutane is just opposite to the direction of the metallocyclobutane formation. So what actually, so here what is happening, so here it is basically just the opposite of the direction. So is a cleavage opposite to the direction of ring formation, okay. Now you will see that this is the new metal carbene center, and it is actually the appended it is appended at the end. So this is again reactive, okay, and then again it reacts with the another monomer, and the whole process repeats, that is the propagation, and then you will get basically the polymer where you have okay like that, and here this one, and as it is this metal carbene is living in nature, so it is if you don't quench it, it will undergo the polymerizations till all the monomers are consumed. You can also forcefully quench it by using a very less reactive alkene, so that it does not undergo the polymerization further, and that is the quenching actually, okay, quenching step, and you get a polymer and you get back your catalyst. So here you will see that reverse ring closing metathesis polymerization, obviously as I told, just a reverse. So it's basically you are get the bicyclic, that is the bicyclic metallocyclobutane through a 2+2 cycloaddition, and then generation of new carbene, okay, by cleavage, and then generation a new carbene, and then that metallocyclobutane undergoes the cleavage by the bond breaking through opposite direction of its formation, and then you it undergoes the cycloaddition reactions with the remaining monomers, and the way the process repeats, and then you get the desired polymer. Okay. So very simple mechanism, very much similar to what we have discussed in the last class when we discussed the ring opening reactions. Okay, and as it is a living polymer, so you can also make the block copolymers. Okay, block copolymers. So if you, that we will discuss in the next class. That is the another advantage of this kind of polymers. Okay. So here you will see, as I told, that as it is living, this one. Okay. So if you add another block, okay, here you will see that this is my, here this is the not bonding, that is actually monomer 1, and here is the monomer 2. So this is the substituted not bonding. So here you will get the this is the leaving end, okay, and you will get your homopolymers. So this is the homopolymer, and once all the monomers are consumed, the monomer 1, then if you add the monomer 2, you will get the block copolymers. Okay. So as it is a living, it is allows the formation to get the block copolymers, and through the successive polymerization of the two different alkenes, and this actually gives the opportunity to make the targeted tailor-made polymers of different repeating units. Suppose if I need a crystalline, not purely crystalline materials, or I need a flexible but some percentage of crystalline, so I can choose my monomer 1 and monomer 2 accordingly, so that I can tune the crystallinity or flexibility or other electronic properties or solubility or processability, or if I need to easily processable material, I can choose the monomer accordingly. So this is very easy way to tuning, as this polymers is very living polymerization, as we also have observed for other like a control radical polymerization like that. Okay. Okay. So this is obviously a very effective way, and that's why, as I told, that it is very popular nowadays to use this kind of catalysts. Okay. And here one example how you can also get a different type of polymers. So far what you will see that this is the linear polymers. Okay. So all here, okay, whatever the linear polymers. Okay. Here is one example how you can also get the cyclic polymers. Okay. Here you will see that this is the cyclooctane. Okay. And you will, once you get the linear polymers, you through the backbiting, okay, you can also get the cyclic polymers. Actually this step is the backbiting step. Okay, the backbiting. So here what we are actually doing here? So we are using the concept of ring opening metathesis polymerization, and then we are doing the ring closing metathesis. Okay, and then and then we are getting a cyclic polymers. The properties of cyclic polymers are very much different than the acyclic polymers. Sometimes sometimes according to the desire or according to the properties, the cyclic polymers are also needed and very interesting. And this is the way how we can make a big cyclic polymers like N is equal to like 50, 60 or 80 like that. Okay, it's very difficult to make a big cyclic polymers, because you will see that to thread, okay, or to make the cyclic, okay, like if you imagine that if I have a alkene here and if I have a long chain, so to thread this one it is very difficult. Okay, so this is the one, the very effective method to make the cyclic polymers, okay, and to make the saturated cyclic polymers, you can easily functionalize, or you can do the further reaction of hydrogenation to get the cyclic alkane. Okay, it's basically cyclic oligomeric alkanes, I should tell. Okay, because the number of carbons are quite huge. Okay, 50, 60, 40 like that. Okay, so this is the another effective method of to make the cyclic analogues of linear polyethylene. Okay. Okay, so not only that one, you will see here that if you take it, you can also make the polyacetylene by choosing the correct monomers. As example, here you will see that this is the again the cyclooctatetraene. Okay, and here you will see that this undergoes the polymerization by the tungsten catalyst. That is the, you will see that this is Stokes alkylidene type of catalyst. Okay, Stokes alkylidene type of catalyst. Here you will see that here these are the three tertiary butoxides, and here it is, you will see that is alkylidene moiety. So this is 1, 2, 3, 6W plus 6. Okay, and here you will see that this kind of catalysts are very effective to make the polyacetylene, and this kind of a polymers are, you know that this is semiconducting in nature. Okay, so very interesting electronic properties. Not only that, you can also polymerize this cyclooctane, okay, by this kind of catalyst to make the corresponding the polymers like this one. Okay, these are very effective polymerization using metal alkylidene catalysts. So not only just a not only the strained alkene, you will see that different type of functionalized alkene or the alkyne that also can be used as a monomer to make more versatile and more functional polymers with interesting properties, which are actually limitations which for different type of other polymerization techniques, as example anionic polymerization or the radical polymerations, control radical polymerization. So this polymerization is very straightforward and very advantageous. Okay, so here another very interesting, okay, the polymerations which can be possible by the metal this kind of carbene or metal carbene or metal alkylidene catalysts. Here you will see that in this case we have used the strained alkenes. Okay, these are strained alkenes. At least some ring strain is present. Okay, so here in this case you will see that these are acyclic. That means no strain here, no ring strain, because this is acyclic. Okay, so even this kind of monomer is also can undergo the polymerization using the suitable catalyst like Graf's second generation or third generation catalyst. Okay, and this is called the ADMT. That means acyclic diene metathesis polymerization. Okay, and here you will get basically the your corresponding monomer and also the ethylene. Okay, for this case. So this ethylene, this exclusion of ethylene is the driving force of this reaction. So if we can remove the ethylene from the reaction mixture, the polymerization chamber, the reaction pathways, okay, the reaction will be more feasible towards the right, and the reaction will be more faster and more feasible. So this kind of reactions, the polymerizations are very much needed to develop new polymers, okay, for pi conjugated materials. I'll give some examples, okay, how it's possible. So you will see that how this kind of a acyclic monomer can also undergo the polymerization using this kind of catalyst. So effective method. So here you will see that how the same concept of the ADMT, that is the ADMT, that is the alkene acyclic diene metathesis polymerization, can also be applied to the alkyne version. So as example, if you understand this one the same thing is basically here also, but instead of alkene, that is the alkyne. Okay, and the tungsten catalyst is basically the same. Okay, same catalyst. Okay, I should also mention here, not only this one, you can also make a versatile polymers like this one. Okay, so it is so effective. I'll give another example that how, okay, you can. So if this is, and so it's basically the hybrid polymers, inorganic organic hybrid polymers, and if you use the same catalyst, okay, you can get this kind of, and why this is polymer is interesting, I'll tell you. Okay, so here you will see that this is conjugated, okay, acetylene is there. Now you will tell that, okay, this silicon, okay, as it is sp3 is not conjugated, okay, but you know that there is a special characteristic for polysilane, that the sigma conjugation is also possible only for polysilanes. So polysilanes is actually semiconductive in nature. So you can make is a hybrid semiconducting polymer. So this kind of polymers are very interesting in the material chemistry for the industries like flexible optoelectronic devices, as example solar cells, OLED, okay, or OFET, like that. Okay, so you will see that this kind of a new type of polymers can be possible by the metal-carbene catalyst or metal-alkylidene type of catalyst. Okay, this is very interesting. Okay, still it is a kind of emerging field. Okay, so there are a lot of things to do. Okay, so here the similar you will see that this is a tungsten catalyst that I showed already the structure, and this is the molybdenum type of alkylidene catalysts. Okay, here you see that by using this you can get the different type of pi conjugated materials, and these pi conjugated materials, as I told, that these are very much desired in the flexible electronic devices type applications. So new type of pi conjugated materials are desired to tune the properties. Here as example, you know that polythiophene is very much very interesting material because it is semiconducting in nature. So this also can be made by the molybdenum based alkylidene complexes, where you see that this is actually the this is the molybdenum alkylidene complexes, actually alkylidene complexes. So here you will see that you are getting a conjugated materials, and obviously in these reactions you will get the n minus number of butane, okay, as a byproduct, okay, in all here everywhere. Okay, this one is called the PPEV. Okay, this is also very popular pi conjugated materials which are widely used for OLED type of application, is also solar cell based applications. Here you see that polyphenylene vinylene polymer, polyphenyl vinylene polymer. So this is the vinyl group actually. Okay, so it's called polyphenylene vinylene. So here you will see that using the molybdenum type of catalyst, okay, and this molybdenum carbene is in situ synthesized in presence of this para CF3 alcohol phenol, and you get your pi conjugated polymers. Okay, and this is very effective, and you get very well defined polymers. And you can, these R groups, okay, you will see that these catalysts are very compatible with this kind of R groups. That means you can change the R groups to polar or non-polar or different, like ester groups, alkyl groups, okay, amino groups, like that. And that's why it's very emerging field in polymer industry and catalysis, organometallic catalysis industry, to use this kind of metal alkylidene catalysts, okay, or metal carbene catalyst to develop new type of polymers. So as a conclusion, you will what we have learned from this one. So you will see that metal carbene catalysts are very effective to get functionalized, okay, functionalized polymers. Okay, you will see here compatible with functional groups, well defined, and leaving polymerization so scope of tuning polymer architecture, that is the properties, and obviously we also learned the polymerization mechanism, which actually undergoes through a mechanism. So, which undergoes through sequential formation of the repetitive formation of the metallocyclobutane intermediate and the cleavage of the metallocyclobutane. Okay. And from here you will very easily understood that how this metal-carbene catalyst has can be used as a very effective catalyst for different alkene polymerization, where the polymerization is not possible by other polymerization protocols due to the different functional groups. So, this metal catalyst, you will see that it has a big future, okay, very bright future, not only for academic laboratories or research, also for it has a bright future and bright prospect for the polymerization industry, materials industry, to use as functional and tunable, okay, polymers, okay, through the alkene polymerization catalysts. So, it is very clear that this, if you choose the right catalysts, okay, and this may be a very effective way to polymerize different type of alkenes, no matter what functional groups are there, what ring string there, or even the acyclic diene or diene, okay, can also be polymerized by using this kind of metal-carbene or metal-alkene catalysts. Okay, so I am very much sure that you are excited to know about this kind of new organometallic catalysts. So, in the next class, I will try to give a summary what we have learned in this course, and what are the future prospect of these metallocenes and the metal-carbene based catalysts in the polymer industries and materials industries. And with this one, I request to study the topics whatever we have discussed following these books. Obviously, the Crabtree book, okay, very much effective. The Hartwig book, Astruc book, and also the basic organic chemistry by Gupta and Elias. Okay. So, thank you very much, and see you in the next class, which is actually our last class. Okay. Thank you very much. See you in the next class.